Hey everybody, day 2 of the video learning. Let's hope that this works out well. This is actually the third time that I've started my video. The do now, you're obviously not going to be able to do number 1, so let's just get rid of that one right there. But you should be able to define limit, and you should be able to define horizontal asymptote and vertical asymptote. Pause the video, do those, and then come back in just a second. All right, cool. So limit, we know that a limit is the value that a function approaches as x approaches a value infinitesimally from either side. And horizontal and vertical asymptote, I would hope that you would have some sort of word like a horizontal line that the function never crosses, or a vertical line that a function never crosses, kind of like an imaginary boundary line. Those things should be in there. Although technically, with a horizontal asymptote, the definition is not a line that it does not cross, because a horizontal asymptote can be actually crossed a whole bunch of times. Vertical asymptote, I'm all right with saying that it doesn't cross, but horizontal is a little bit different. There are a couple things that I wanted to note here. First, those slides didn't really apply to you. But this was a ticket out the door that I got a few years ago when we were talking about defining a limit. And somebody wrote down a limit is the value the graph approaches infinitely from both sides without ever reaching it. And the problem that I have with this one is the word approaches infinitely from both sides. Infinitely means massively huge. All right. So in order for it to approach infinitely from either side, it would have to approach really bigly from either side. What we really want to use here in place of infinitely, because we want it to be as you get really, really small close to that x value, we want to use the word infinitesimal. Infinitesimal means so small you can't recognize it. It's kind of like the inverse of infinite. All right? And down here we have explain the difference between input value and function value. Input value is the leftiness, rightiness. Function value is the uppiness, downiness. So how far out versus how far up. X value, function value. All right? Input value, function value. Those are things that you need to know. So man, wind just knocked my door shut, and you saw me jump probably there. That's because the wind blew my door shut. Yikes. Okay, so for fun, let's say that f of x equals 1 over x. I've got the graph drawn right over here for you. You might want to draw that in your notes. We are trying to figure out four different limit values. Limit as x approaches positive infinity of 1 over x equals. Limit as x approaches negative infinity of 1 over x equals. If you printed out my PDF and you're trying to make notes on that, this one is left off there. I just forgot to put it up here. We also want to know the limit as x approaches 0 from the right, because we have that plus after the 0 of 1 over x, or the limit as x approaches 0 from the left of 1 over x. And there's a couple of ways that we can approach this. The first way that we can approach this is, of course, graphically. I will point out that up here, we don't have, I guess we could do numerically, but algebraically is not really an option right now, because we're dealing with a number called infinity.
Just let you know that it's not unique to us, that as far as we can tell, it's out all the way to strong Vincent. So it's something within the city and not unique to Cleveland.
I'm going to leave that in there. That's Mr. Vieira telling us that the internet is out across the city, apparently. That means no distance learning. Luckily, I don't have any students right now, so I'm cool. Okay, so we got the limit as x approaches infinity of 1 over x. That's where I was. We're talking about infinity. So you can't actually deal with infinity as a number because it's not anything that we can comprehend as humans. So we kind of have to transcend our human capability. So one thing that we can do, limit as x approaches infinity of 1 over x, we're just going to travel on this graph toward infinity. Now note that we're talking about positive infinity over here. Positive values go to the right. To the right, to infinity. Infinite to the right is as far as you can go to the right, and then further, and then even further, and then even further. Basically what we're just asking is, what happens to this function as it goes out here? And that function, we know from trig precalc, that function has that HA word, horizontal asymptote, at y equals 0. So if I was to go all the way out to infinity, the height of this function would reach a height of nothing. 0. Same thing over here. Limit as x approaches negative infinity of 1 over x. We're going to go all the way to the left. And as we go to the left, we have the same horizontal asymptote at 0. Now, this is probably not a good way to evaluate limits at infinity because you have to remember everything from trig pre-calc. Remember how to determine your horizontal asymptotes. There were those 3 rules that we had. If the degree was smaller, if the degree was in the numerator was smaller than the degree in the denominator, then y equals 0 as a horizontal asymptote. Degree is the same, you divide lead coefficients. Degree is bigger on the top than on the bottom, then you have no horizontal asymptote. Who really remembers all 3 of those other than me? Well, maybe some of you do. Next thing we look at, again, we're doing just a strictly graphical approach. The limit as x approaches 0 from the right. Well, from the right, that's this side, and I'm trying to approach. Let's put this back on Active Inspire so we can see it a little bit better. That's one thing. My mom reviewed my last video, and she said when I was standing at the board, you couldn't really read it. So I'm trying to get the Active Inspire for you guys to read. We can see our approach values at 0, and coming in from the right, we just go up-a-doodles. And up-a-doodles is toward the top. If we think about how uppy-downies work, that's a positive value. And going up and not stopping, we call that increasing without bound, means the value is infinity. So just the graphical of it going up at that, let's use another vocab term, at that vertical asymptote. We remember that whenever we have 0 in the denominator, we have a vertical asymptote. The trouble that we have is, does it go up or down? And really right now, all we're doing is we're looking at it graphically to see whether the graph goes up or down. Coming in from the other side, the limit as x approaches 0 from the left. Let's pull this graph back up here, and we can see graph go down. And it never stops going down because we have that vertical asymptote again. So this will be downsies is a negative infinity. So that's the graphical approach there. We could also do a verbal approach, all right? So a verbal approach right here, limit as x approaches infinity of 1 over x. That's like taking a really big number and defining a finite number divided by the really big number. So I find that this works best when we talk about sharing food or sharing money. Let's just say I have a cookie. If I have that one cookie, I'm going to get one cookie. If I invite one of you into my room, we're each going to get half of a cookie. 3 people, we're going to get a third of a cookie. If I invite the entire class into my room, let's say there's 20 people, we're each going to get 1/20th of a cookie, which is pretty small. When we increase that number to, let's say the school, 700 people, we're going to get a 700th of a cookie, which is even smaller. City of Erie, about 100,000 people, we're going to have 1/100,000th of a cookie, which is practically nothing. The problem is we can never share with infinity people, so we're never going to quite get down to having no cookie whatsoever. But if we share this with like the entire population of the Earth, we're probably each going to get 1 molecule of the cookie. So, negligible amount of the cookie. Same works with negative infinity. The difference here, for me to decide whether it's a positive infinity or a negative infinity, the division rules still work the same. So positive divided by positive infinity gives me that positive 0, the 0 above the x-axis. Down here, we talk about positive divided by negative infinity would be that negative 0, or that approach value from below the x-axis. We can do the same thing down here on limit as x approaches 0 from the right, or limit as x approaches 0 from the left. We look at this as 1 divided by 0. Well, you're not allowed to do that. But we want to make this value approach 0 closer and closer to 0. As we make the denominator smaller and smaller, if you think of how fractions work, make your denominator smaller means make your fraction bigger. As I make my denominator smallest possible, this should be biggest possible, which would be infinity. And again, our division rules work the same. So 0 from the right would be positive 0. Positive divided by positive gives me positive. Positive divided by negative 0 gives me that negative infinity. Say that it's shooting down. Another way to look at this would be that numerical approach. So if I take out my calculator, and I apologize, I did not actually pre-populate this in my calculator. So I'm gonna have to clear out all of these guys right here. And let's just do 1 divided by x. If I go up to my table, I can actually see how that's gonna work. Like, let's say I'm talking about that first limit where I talk about the limit as x approaches positive infinity of 1 over x. Positive infinity, I could try 9, then 99, then 999, then 9,999. And see, as I add more 9s, making them really big, the number here gets close, the output, the function value, gets closer and closer to 0 until I get ridiculously big. That becomes 10 to the negative 19th power, essentially 0. I can do the same thing when I talk about negative 9999999. Gives me negative 10 to the negative 13th, which would be essentially that negative 0. We can do the same thing if we want to, doing it numerically, getting closer and closer to 0. So here I start at 0.1, 0.01, and as I get closer and closer, putting more and more zeros in there, I get a bigger and bigger value until I get really, really tiny. Gives me really close to 0. 9.1 times 10 to the 25th. Sorry, not really close to 0. Really big to big. Really close to big. Like infinity. Versus if I go with the negative side of all that, negative 0.1. Whoopsies. Whoopsies. Negative 0.1. Negative 0.01. Negative 0.001. And you can do the numerical approach there. Approaching from both sides to see, well, in this case, not really approaching from both sides. It's just doing those handed limits. I will point out that if I'm talking about overall the limit as x approaches 0 here of 1 over x, that does not exist because one handed limit is positive infinity, the other handed limit is negative infinity. All right, let's take a look at a couple of other limits. Limit as x approaches infinity of e to the x minus 3. Limit as x approaches negative infinity of negative e to the negative 4x power. What I like to do in these types of problems, I like to just stretch my brain a little bit. Something that I'm not supposed to do is like a direct substitution. I can't really do direct substitution because this is infinity, but I'm going to play like I can. E to the infinity minus 3. Let me put this up here, just like my mom suggested. I now have that, right? Again, you should not write this out in any sort of formal paper, but this allows us to evaluate limits at infinity a lot easier. E to a power is big. E to the infinite power is really big. This is not big. So big minus not big is going to give us still big. What I'm trying to say here is e to the infinite power is essentially infinity. If you get an infinite value and you take off a finite, you know what you have? Still infinity. So anytime we talk about infinity, if we take off a finite power, a finite amount, it's still going to be infinity. Over here, I look and I see that I have limit as x approaches negative infinity of e to the negative 4x. What I like to look at on this one, again, I try to do my, and you guys can't see it, let me flash it, direct substitution. It's not really direct substitution since we're talking about infinity, but I write it out anyway. Although I probably wouldn't write this out, I would just think this in my head. I now have negative e to the negative 4 times negative infinity. Well, negative 4 times negative infinity, negative times negative gives me positive. This becomes e to the 4 times infinity. Well, funny thing about infinity, infinity is infinite. It means it's not countable. 4 times not countable is also not countable. So this value up here is going to be infinity. And e to the infinity, just like we were talking about over here, e to the infinity is just really big. But since I have this negative out here, it's really big in the negative direction. All right? Sounds like fun? There was something that I did want to point out on this previous page right up here, where we have the limit as x approaches infinity of 1 over x, or the limit as x approaches negative infinity of 1 over x. This type of strategy where this equals 0 is correct. Whether we have 1 over infinity, 2 over infinity, any finite number. We could have the limit, let me just make up a limit right here. This limit. The limit as x approaches infinity of 10 to the 20th power over x. Because 10 to the 20th power technically is finite, I can count to 10 to the 20th power. I don't want to, I can. This would be 0, as long as you have finite divided by infinity. So if I was taking notes on this one, and I think my dot cam turned off when we lost power here a minute ago, but if I was taking notes, I would make an acknowledgement that, come on dot cam, limits at infinity. Ah, there it is. Haha, there we go. Took a minute, but it got there eventually. Limits at infinity. If you have finite in the numerator and infinity in the denominator, that equals 0. If I have finite in the numerator and infinity in the denominator, oh, not the same exact thing. Finite in the numerator and 0 in the denominator, that's going to be infinity. Essentially what I'm trying to let you guys in on the secret for is 0 and infinity are reciprocals of each other. When you divide by 0, you get an infinite value. When you divide by infinity, you get a 0 value. Hey, who knew? We already did these. It looks like we good? All right, cool. This leads us to the calculusy definition of both horizontal and vertical asymptotes. Those are going to be on your book on page 70 and page 72. And just because I want to, I'm going to put those up here. All right. So there's the technical definition of horizontal asymptote. And because we have the words to describe things using limits, we now have the tools to be able to describe what a horizontal asymptote is. And the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b. And you can see right down here, there's a nice example. The limit as x approaches infinity of 2 plus 1 over x is equal to 2. The limit as x approaches negative infinity of 2 plus 1 over x is also equal to 2. So this has a horizontal asymptote of 2. And we'll go back and we'll calculate some of these limits to actually figure out the horizontal asymptotes without just being told, trust me on this one. But trust me on this one, that is the only horizontal asymptote for f of x equals 2 plus 1 over x. And now switching up to the, and just to explain this a little bit, we talked about limit as x approaches infinity as going all the way to the right. Going all the way to the right is finding that horizontal asymptote. X approaches negative infinity, that's going all the way to the left. So that's, again, that horizontal asymptote. And try to bring it back to that picture that we had on that first slide there. Now on page 72, we have vertical asymptote. The line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x approaches a from the right of f of x is either equal to positive or negative infinity, or the limit as x approaches a from the left of f of x is equal to positive or negative infinity. And I would write that down if I were you. I would also advise you that when we're talking about this, we're talking about as you approach a value, the function goes either up or down. And that's coming in from the right. Coming in from the left, function either goes up or down. And that's going to be our vertical asymptote, where it kind of shoots up and infinitely approaches that asymptote. And again, we'll calculate some of these limits to try it out in a minute. But before we get there, let's go back over to, nope, not that. Turn off the sphere. Let's explore a case of horizontal asymptotes. All right? We've got the limit as x approaches infinity of 2x squared over the square root of x to the fourth plus 2. We've got the limit as x approaches negative infinity of 2x squared over the square root of x to the fourth plus 2. Now, I will tell you that we're talking about horizontal asymptotes, and I can tell we're talking about horizontal asymptotes because we're talking about the limit as x approaches infinity and the limit as x approaches negative infinity. For vertical asymptotes, the approach value would be some sort of finite value, wherever the vertical asymptote is. So since our approach value is infinite and negative infinite, we've got horizontal asymptotes. We're going to explore this a couple of different ways. For the graph, I want to use a window of negative 100 by 100 by negative 3 to 3. All right? So if you've never read anything like that, put this back up here and put the calculator. Let's see if I can move this calculator. Trying to move the calculator. There we go. There we go. Just so that we can see the function at the same time and our viewing window. All right. So the viewing window, the way that I have this set up, I go into window, and this negative 100, that's referring to the x min, so negative 1 hundo to positive 1 hundo, and negative 3 to 3 down here. Down here. I'm trying to refer to that as my y min, so negative 3, and my y max positive 3. I might make my x scale something other than 1 so that I don't have to count from negative 100 all the way up to 100 by 1s. Let's count by 10s. And now I'm going to graph. Remember, we're trying to analyze what is our horizontal asymptote. Oh, helps if before we do that, we actually put the function in there, doesn't it? Like, oh man, that doesn't look anything like what I thought it was supposed to be. So, alpha, y equals fraction 2x squared over second square root x to the fourth plus 2. And now I can look at my graph and I can see, well, golly gee, it looks like that levels off. And what's it look like it levels off at? To me, that looks like a 2. But again, we're doing this graphically, so graphically is pretty much the worst way to do it. We could try to get a feel for it by doing this numerically. And the good thing about numerical approaches in this type of problem, you don't actually have to worry about from both sides, because really, there's only one side of infinity. And that's, you're going to infinity, you're approaching from this side. If you're going to negative infinity, you're approaching from this side. So we don't have to talk about handed limits. If we're trying to talk about the limit as x approaches positive infinity, to be honest with you, all I do is put in a really big number. Does that look like a really big number to you? It does to me. It's just a bunch of 9s. And look, when I put 1 times 10 to the 16th, I get 2. And for negative infinity, I put in the other one. 2. Unfortunately, we're not always going to have our calculators. So if we don't have our calculators, there's actually, I think it's an easier way to do this. but it requires a little bit of mental gymnastics, and sometimes people don't like it. So what I look at when I'm talking about this one, I see that I direct substitute in infinity, and I get this is infinity to the fourth. Infinity to the fourth is really big. 2 is finite. I look at this and see that I have in my denominator really just the square root of x to the fourth. My numerator, I'm still going to have that 2x squared. Really what I'm looking for here is knocking off what we call the least contributing terms. My least contributing terms are just the numbers in the addition problem, which aren't that significant. So that plus 2 means nothing to me. I now have 2x squared over the square root of x to the fourth. And now this becomes limit as x approaches infinity of 2x squared over square root of x to the fourth. Well, when I take the square root of x to the fourth, I'm left with x squared. X squared and x squared drop off. I have the limit as x approaches infinity of 2. And that's just the value. No matter what I plug in for x, I'm going to get 2. So this is just going to be 2. I would do the same thing down here. Again, I'm knocking off the least contributing terms, and that least contributing term is still that 2. So I get 2x squared over square root of x to the fourth. I'm left with limit as x approaches negative infinity of 2x squared over x squared. Cross off the x squareds, and we're left with limit as x approaches negative infinity of 2, which again, there's no x values in there, so the limit value is just 2. I'm going to put up my beautiful handwriting so you guys can see that. Some things to note here is until, and you can't see my air quotes because my webcam's not on right now, but when I do the d sub, that's when I drop my limit notation. All throughout here, I was just thinking algebraically until I hop over here to get the 2. So I have limit notation in those previous 3 steps. Now let's make sure we got that right. Did we get it right? Yeah, we got it right. All right, cool. Now, let's use the sandwich theorem to figure out what the limit as x approaches infinity of sine of x over x squared is. Now again, people hate the sandwich theorem. I don't really know why. I happen to love it. It's really cool how it works. I'm trying to figure out what is the limit as x approaches infinity of sine of x over x squared. Well, I have no idea. No clue what this value is. But I do see that trig function. And one of the tricks that I told you in the last section is whenever we're dealing with the trig function where we don't know what the value is for that limit, we might use the sandwich theorem. Since this one says use the sandwich theorem, we're going to use the sandwich theorem. So I start with sine of x. Since it says use sandwich theorem, I know that I need to have a top bread and a bottom bread. Sine of x is always bigger than or equal to -1, and it's always smaller than or equal to +1. Now I look back up here at my function that I'm dealing with. I'm not just dealing with sine of x. I'm talking about sine of x divided by x squared. To get sine of x divided by x squared here, I'm simply going to divide it. Since I divided by x squared on one side of the inequality, to maintain inequality, I divide it everywhere. So I introduce a divide by x squared everywhere. Well now, look, I have that matching. All I have to do is apply the limit. As x approaches, it was infinity in the original problem, so I've got the limit as x approaches infinity of sine of x over x squared. And here's really the only calculus-y part of the limit of the sandwich theorem. Sandwich theorem says if I apply limit on one side of the inequality, I have to apply it on all 3 sides. So now, I'm doing limit as x approaches infinity of -1 over x squared, and the limit as x approaches positive infinity of +1 over x squared. Well, now again, I still have no idea what this is. But if I go for that direct substitution type thing, I know now that I have finite -1, I can count to -1, divided by infinity squared, which is infinite. I go back to the notes that I told you guys you should probably have. Right here. Finite divided by infinite, well, that's just 0. So this is 0. Over here I've got finite. I can count to 1. 1, I just did it. Divided by infinity squared, so that's infinite. Finite divided by infinite, that is going to be just 0. And now, I don't know what the limit as x approaches infinity of sine of x over x squared is, but I happen to know, again, bringing it back to this number line, since we're talking about the or equal to on the inequalities, we'll put 0 in the center of my number line. This value is somewhere in between 0 and 0 inclusive of 0. I would just go with, therefore, the limit as x approaches infinity of sine x over x squared is equal to 0. And that's not supposed to be a dollar sign. I wasn't trying to be gangsta about it or anything. I just accidentally started misspelling sine. Right? Sandwich theorem. It's fun. The next thing that we have here is we have theorem 5 on page 71. And theorem 5 is way more complicated than it needs to be. Page 71. Here's theorem 5. Right? And you can have that in your own book if you want to. L, M, and K are real numbers. Obviously, the approach values in this situation are not real numbers because we're talking about infinity, and that's not real. It's just saying all of those rules that we had before, like the sum rule, they work with infinity as well. If you have a limit of sums, you can change that to the sum of the limits. Difference rule. If you have a different limit of differences, you can take the difference of the limits. Product rule. You can split a product within the limit into a product of the two limit values. Constant multiple rule. You have k times a function. Any number times a function. You can just do that number times the limit value. Quotient rule. Limit as x approaches infinity or negative infinity. Quotient, f of x divided by g of x. You can just do the function values as long as the denominator is not equal to 0. And power rule works just the same. There is one other limit, I guess, that is sometimes tricky, and I kind of used it just a minute ago. I have seen people have difficulty with this one before, but again, if k is just a number, then the limit as x approaches really any number, but let's just talk about positive or negative infinity of k is equal to k. And the application to that is like the limit as x approaches positive infinity of 7. If there's no x value, that's just equal to 7. Because the function here is just a horizontal line, so the function value is always going to approach 7. Let me pull up some examples of limits. You might want to pause, get that theorem into your notes, but I'm putting back up this. Okay, cool. So we've got all these problems up here. Limit as x approaches infinity of 3x squared plus sine x over x squared. We can actually do this pretty easily. What I look at here is I see that I have a sum in the numerator, so I can split that up into two different fractions. I end up with the limit as x approaches infinity of 3x squared over x squared plus sine x over x squared. And now, since I'm talking about a sum, I can talk about this rule right here. I can rewrite this limit as limit x approach infinity of, well, let's just knock off those x squareds, right? Numerator and denominator. As long as I know how to do algebra, I know those cancel off. Of 3 plus the limit as x approaches infinity of sine x over x squared. Well, that last property that I just enumerated for you guys, the limit as x approaches really anything of just a constant is said constant. Well, that works beautifully right here. We just have 3 plus whatever the heck this is. But I don't know what this is. Those of you following along at home, recognize that that's this problem right here, one that we just did. So I know that this value is 0. Limit as x approaches infinity of 3x squared plus sine x all over x squared is equal to 3. And then you're done. Now you can graph that in your calculator, and you can actually see that the horizontal asymptote of 3x squared plus sine of x all over x squared is going to be 3. And it's fun to try that out. Try these other problems out, pause the screen, and then come back to them. I mean, right now, I'm coming back to them. If I was looking at these, I really don't like to write it all out like this. What I look at is, well, I've got the limit as x approaches negative infinity of 2 over x. That value right there, I know since I've got finite in the numerator, infinite in the denominator, that's going to be 0. Here I've got limit as x approaches negative infinity of 1. Well, that's just a constant, so that's 0 plus 1 times the quantity. Oof, man, I'm going to split this up. I'm just going to make a little bit of notes up here. We got 5x squared over x squared minus 1 over x squared. Split up that sum in the numerator. As long as the sum's in the numerator, you're allowed to do this. I can see those x squareds cancel off, and now all of a sudden I have 5, because there's no x squareds here, minus, well, finite divided by, again, I'm plugging in infinite, so that's 5 minus 0. I have 0 plus 1 times 5 minus 0. That's 1 times 5. 5. You can do some of these in your head, I would imagine. I mean, like here, I plug in infinity. Well, this is kind of weird because I've got cosine of 1 divided by infinity. I keep pointing with the wrong end of my pen, so I apologize for that. Cosine of 1 over infinity, well, I happen to know if I have finite divided by infinity, that's just going to be cosine of 1 divided by infinity. Say it along with me at home. 0. Divided by 1 plus 1 divided by infinity, again, is 0. I end up with cosine of 0 divided by 1 plus 0. Well, I happen to know 1 plus 0 is 1. Some of you might need to go back and revisit your unit circle to figure out what cosine of 0 is. I happen to be able to look at my unit circle clock that's hanging on my wall, and I happen to know that if I was to just sketch the unit circle right here, I know that 0 is right over here, and I know that that coordinate is 1 comma 0. Nice little life hack for y'all in calculus. Sometimes we do go outside of the first quadrant, but in general we stick to the first quadrant. There. But looking here, I see my x value is 1, so cosine of 0 is 1. Divided by 1, I got that value is 1. Horizontal asymptote going off to the right for this function is 1. And you can graph it, and you can see that it actually has a horizontal asymptote. And last one that we have here, this is really just kind of weird. I would have to informally really do my sandwich theorem on this one. As I look at this, I've got 5x plus sine of x. Well, if I plug in infinity for x, I'm going to get 5 times infinity, which is infinity, right? I know that sine of x is somewhere between -1 and 1. All the numbers between -1 and 1, they're finite. You can see that quantity. So I know infinite plus finite is still going to be infinite. This is what we call insignificant. In this type of problem, I would just say BISOs to sine, and this ends up being the limit as x approaches infinity of 5x over x. Cross off those x's, I end up with limit as x approaches infinity of 5, which is itself just 5. Again, we'll practice with some of these problems in class tomorrow, but you can really whip through these problems as fast as possible. Let's make sure we get them all right. Did we get them all right? Did we get them all right? We got them all right. We got them all right. All right, cool. So N behavior models. An N behavior model, a right N behavior model, a function G is a right N behavior model for f if and only if the limit as x approaches infinity of f of x over g of x is equal to 1. And it is a left N behavior model for f if and only if the limit as x approaches negative infinity of f of x over g of x is equal to 1. That's a bunch of fancy stuff that we have going here, and we'll get back to these N behavior models. This is really just saying, like, what does a function look like as we go to the end? And it's not hard to figure out an N behavior model. When I look at the N behavior model for this function, and it really just tells me, like, whoopsies, wrong way, you ignore that. it tells me if I go off to the right, is the function going to go up or is it going to go down? Does it go off to the left? Is it going to go up or is it going to go down? And looking at these end behavior models, I can figure that out. Basically what I look at here is this function. As I go to the right, the only thing that is significant about this, again, going to the right is going to mean x is going to go to infinity. I have infinity to the fourth power, which makes 3x to the fourth negligible. 2x squared, negligible. X, negligible. 5, negligible. The right end behavior model, let's just call this h of x, is going to be 2x to the fourth. And you can check this by comparing these two values. In fact, let's just check it real quick. Limit as x approaches infinity of, let's put the more complicated function up top, just because that's going to be better for us, plus 3x cubed minus 2x squared plus x minus 5 all over 2x to the fourth. All right? So when I look at this, I can split this up into 1, 2, 3, 4, 5 different fractions. It's going to end up being the limit as x approaches infinity of 2x to the fourth over 2x to the fourth plus 3x cubed over 2x to the fourth minus 2x squared over 2x to the fourth plus x over 2x to the fourth minus 5 over 2x to the fourth. This one becomes 1. Right here, we end up with 3 over 2x minus 2's cancel out, 1 over x squared plus 1 over 2x cubed minus 5 over 2x to the fourth. When I'm proving this, I see I've got 1 plus finite over infinite, 0, minus finite over infinite, 0, finite over infinity, 0, finite over infinity, 0. Now 1 plus 0 minus 0 plus 0 minus 0. That equals 1. By the definition on the previous page, we see that the end behavior model is 1. And this particular problem, it works in both directions. Now with this g of x, same deal. Just pick your biggest contributing term. End behavior model. We already used h of x. J of x is equal to 3x to the 6th. Now I'm not asking you to confirm what the end behavior model is, just write it down. And what this tells me is this function up here behaves like a quartic. It goes up in either direction because because the lead coefficient is positive. Down here, this behaves like a sextic. It goes up in either direction as we go to infinity. Now there are some other more, I guess we might call them complicated end behavior models, like this one. This has two, this one right up here. This has 2 end behavior models. It has right end behavior model, and it has left end behavior model. The important thing to remember is as we go to the right, that means x is approaching infinity. If I plug in infinity here, I'm going to have infinity plus e to the negative infinity. That's like x plus 1 over e to the x. If I plug in positive infinity, this is going to be 1 over infinity, which again, we learned today is 0. We have infinity plus 0. This is the bigger contributing term. The right end behavior model is y equals x. This function behaves like a linear function as we go off to the right. Now, the left is a little bit different. If I plug in negative infinity here, this now becomes e to the negative infinity. Negative infinity is positive infinity. We have negative infinity and infinity. This is much bigger. This is saying that this function behaves like that decay function, that y equals e to the negative x as we go off to the left. Now what about rational functions like this? These are actually pretty easy. End behavior model is just going to be y equals biggest contributing term from the top divided by biggest contributing term from the bottom. Simplify x fifth x squared, we get 2/3 x cubed. And then we're done. Right. Gotta be approaching the end here. Ooh, all else fails. Just think it through. This one, we kind of did this before. I mean, you could plug in limit as x approaches infinity. You got 1 divided by infinity, you get 0 inside there. It's also possible whenever we're dealing with these values, you can say that this is equal to the limit as x approaches the reciprocal of infinity. Reciprocal of infinity would be positive 0. So we're talking about limit as x approaches 0 from the right. And if this was negative infinity, we'd change this to 0 from the left. Of cosine, if you use this approach, you're just going to take the reciprocal of wherever you see x. So of cosine of x. So this is equal to the limit as x approaches 0 from the right of cosine of x. Since cosine of x, it's the same from the left or the right. It's either one of those. This is just going to be cosine of 0, which is equal to 1. I don't really like this approach. This one's just a little bit too weird for me. So I just like to d sub in the infinity and get the cosine of 0 right off the bat. But it's up to you. You might be different from me. Let's see. Yeah, we made that good. Ah, cool. So now here's the assignment that we're really going to be focusing on in class tomorrow. Feel free to look around at it, find the ones that are the hardest. You'll have to know where the int function is on the math menu. So this was fun. Let's do this again sometime. Bye.